Hello, this is John from caveofprogramming.com. In this tutorial we're going to take a look at perfect forwarding in C++. I wanted to make a video on this just because although this isn't something that you really need to use a lot, it's something that's often mentioned in the context of C++ 11. So I thought we should have a video on it here. So let's suppose we have some sort of type declaration here. So we're going to use auto. And I'll just call this variable t, and let's set it equal to test like this. So if I try to compile this, it does work, and there's no real surprise there. So the type auto here could just be test, and so we get a R value reference, and this is an R value. No surprise there, but let's create a L value, which I'll call test, and then try to point this reference variable at it. So if I compile this now, it also compiles. Now t here can't be an R value reference because then it wouldn't bind to an L value. And in fact there's a rule in C++ 11 that says if the auto here boiled down to a L value reference type, then the references as a whole would collapse. And what would be left with would be an L value reference, which is why this can bind to an L value. So this is a reference. This is one of the reference collapsing rules for C++ 11. Not something that you really need to think about a lot, but they exist. Now let's take a look at an example of a type declaration, a template declaration that uses R values. Sometimes you want to have a template type, let's say template here, and I could use class or I'll use type name. They're both equivalent here. So type name t, and let's say void call, and I'm going to create an argument here, and I'm going to make it t R value reference arg, like that. And then I'm going to call this check function here. And I've got two overloaded versions of check. One will tell us if it gets past an L value reference, and the other will tell us by getting called if it gets past an R value reference. There's no easy way that I know of to tell the difference between an L value and an R value in C++ 11 except by calling functions, overloaded functions where you get the right one being called depending on what argument you get passed. So let's call check with arg like this. Now the idea behind perfect forwarding is that you might want to call the right version of a function depending on whether you passed to your template function a R value or an L value. So in other words, this argument here will get passed in as an R value or a L value, and as we saw with this thing here, it could actually be either. We could call this function with an R value or an L value because we're going to end up with a type t being inferred that just makes it work. And then we might want to pass on the argument in such a way that its L value or R value-ness is preserved, and we can do that with perfect forwarding. So the way this works is this at the moment I don't think is going to work because within this function arg looks like an L value. So we could take the address of arg within this function, and that means we're going to get the L value version of check being called. So let's check that actually works. So I'm going to say call, and let's pass in an R value like that. So here I've got the template type being inferred as we saw in an earlier lecture. Let's run this, and we see that we get the L value version of check being called. So here we haven't got perfect forwarding. Here we're passing in an R value, but then we're calling this function here and passing it an L value, and sometimes you want to pass on whether it's actually an L value or an R value that you pass to the function. Same thing happens if we pass it a L value like this. We also get the L value version of the function being called. But we can fix that with a static cast. So I could do static cast t and pass in arg. And now, because we're making use of the inferred type that was called, we can end up calling the right version of check here. So here we've got L value, but if we pass call a R value, then we end up, excuse me, we end up passing this on as an R value. So what's happening is that if we pass in a L value here, the inferred type is going to be T reference, and reference collapsing works in such a way that we end up with a L value here. If we pass in an R value for T, then we're going to get T being inferred just as a kind of L value type, and then T reference is then an R value. So I think I said that the right way round. Now there's a little function called forward, which makes this a bit easier. So if we just type forward in here, forward is just, it really does the same thing, but it's just kind of intended for using in this particular circumstance. So if we run this now, here we get the type being passed on as R value, but if we called this with an L value, we'll get the type being passed on as L value. So this is pretty complex, and if you feel it's too much for you, then I don't blame you. It's taken me quite a while to get my head around this at all. It's not something so far in my entire career. Well, C++ only came out, 11 only came out in 2011, so I haven't needed to use this yet. But if you have the motivation, it's a good idea just to verify this for yourself. And you might want to also Google reference collapsing C++11 just to have a look in a bit more detail about how that works. But the bottom line is that this type can be inferred in such a way that we end up here either with a R value reference or an L value reference, surprisingly. And that's because if T is actually an L value reference, the result as a whole, surprisingly, is an L value reference. Okay, so that's it for this tutorial. Just something that's worth having a go at yourself and just playing with. And it's by no means certain, even if you work as a C++ developer, that you're ever going to need this. But it is used internally, for example, in various places in the C++ API. So it's kind of worth at least having a nodding acquaintance with, I think. Okay, so until next time, happy coding.